Hi, my name is Connor Patterson, and today I will show you a step-by-step tutorial of how to complete Chapter 6.6, question number 10 on page number 362 of the Nelson Advanced Functions textbook. The question states, the number of hours of daylight in Vancouver can be modeled by a sinusoidal function of time in days. The longest day of the year is June 21st, with 15.7 hours of daylight. The shortest day of the year is December 21st, with 8.3 hours of daylight. There are two parts to this question, A and B. A states, find an equation for n of t, the number of hours of daylight on the nth day of the year. And the second part to the problem, B, states, use your equation to predict the number of hours of daylight in Vancouver on January 30th. The very first sentence of the problem, modeled by a sinusoidal function of time, tells me that the question will be solved using our knowledge of Unit 4. As in this unit, we learned how to create sinusoidal functions when given properties such as max value, min value, period, and equation of axis. With the question being from Unit 4, we can use our knowledge to interpret the information given to us. The number of hours of daylight in Vancouver can be modeled by a sinusoidal function of time, in days. The first sentence outlines that we will be working with a sinusoidal function, and the t value in the equation will be represented in the unit days. The second line of the problem states, the longest day of the year is June 21st, with 15.7 hours of daylight. This line of the question is telling us the maximum value for the sinusoidal function is at 15.7 hours and happens on June 21st. The last line states, the shortest day of the year is December 21st, with 8.3 hours of daylight. What this line tells us is that the minimum value of the sinusoidal function is at 8.3 hours on December 21st. To recap number 10, we have figured out that we have to use a sinusoidal function and equation to solve the problem. We are given the maximum value at 15.7 hours and the minimum value at 8.3 hours. After properly analyzing this question, we can now begin on working on part A. In order to solve for part A, we must first analyze the problem it presents, and second, create a plan in order to solve the problem. So first, let's read over part A again. Find an equation for n of t, the number of hours of daylight on the nth day of the year. Next, we must create a step-by-step plan on how to solve this problem. The first step of solving this problem is to extract the key values given to us in the question and the ones that will be used in the equation. As you can see, we have the max value of 15.7, which was given to us in the equation, and the min value of 8.3, which was also given to us in the equation. Using these two values, we can solve for the k value of the equation. In order to solve for k, we must first have to understand what k represents. K is also equal to the equation of axis of the sinusoidal function. In order to solve for k, we must use the equation k is equal to max plus min divided by 2. Since the max and min values were given to us in the question, all we need to do is plug them into the equation. Therefore, we get k is equal to 15.7 hours plus 8.3 hours divided by 2. K is then equal to 24 hours divided by 2. K is equal to 12. Therefore, the equation of axis is equal to 12 hours. The next step to solving this problem is to solve for b. We know after learning class that b is equal to 2 pi divided by the period. Since we are dealing with days of the year, the period for this problem will be the amount of days that are in a year. This I know is 365 days. Now we can solve for b, and b is simply just 2 pi over 365. The second step to solving this problem is to determine which primary trig ratio we need to use for creating an equation. For this problem, I determined that I want to use cos for my trig ratio. This is because the question gives us the max value and when it occurs. Therefore, I can find the phase shift easier than if I chose to use a sine function. What I've done next is I have recapped all of my known values and plugged them into the equation. As you can see, I have my b value of 2 pi over 365 and my k value of plus 12. The third step to solving this problem is to find the phase shift or h value for this cos equation. To do this, we need to set one day of the year to equal to day 1. For this problem, I let January 1st equal day 1. Because we are using a cos equation, we need to solve for how many days pass between January 1st and June 21st. This is equal to 172 days. Therefore, our h value is equal to 172. The fourth step to solving this problem is to sub in a point into our equation to solve for a, which is step 5. And in addition to the max value of the year, it also gives us the min value of daylight for the year, which is on December 21st. So this is the point I will use to sub into my equation. Recall that our minimum value for the sinusoidal function occurs on December 21st and is at 8.3 hours. This will be the point that we can sub into our equation in order to solve for a. I know that December 21st falls on the 356th day of the year. Therefore, t is equal to 356, and 8.3 hours will be our n of t value. After subbing these two values into our equation, we now get this new equation. 8.3 is equal to a cos of bracket 2 pi 365 bracket 356 minus 172 double bracket plus 12. The first thing I've done in order to simplify this equation is I have brought the k value over to the other side of the equation, subtracting 12 from 8.3. I have now, in this line, simplified what is in this bracket, subtracting 172 from 356. After multiplying our two values inside the bracket, I have now reached the equation negative 3.7 is equal to a cos bracket 368 pi over 365 bracket. To reach this next line, I have taken the cos of 368 pi over 365. The next step to solve for a is to divide both sides by negative 0.99967. After dividing both sides of the equation by negative 0.99967, I have determined that the a value for this equation is equal to 3.7. Therefore, the sinusoidal function for this problem is n of t is equal to 3.7 cos bracket 2 pi over 365 bracket t minus 172 double bracket plus 12. Now, after we have solved for part A, we can begin to read part B. Part B states, use your equation to predict the number of hours of daylight in Vancouver on January 30th. Now we must create a step-by-step plan of how to figure out this problem. The first step to solving the problem is to figure out what day of the year January 30th falls on. Step 2 into solving this problem is to sub in the day in which January 30th falls on as the t value for our equation. The last step in order to solve for part B is to simplify our equation to solve for n of t, or the number of hours of daylight in Vancouver on January 30th. Before beginning to solve for part B, we must recall the equation that we have created in part A. Step 1 to solving a problem is to figure out what day of the year January 30th falls on. Again, we must let January 1st equal to day 1. Therefore, January 30th is equal to day number 30. Step number 2 is to sub our value of t into our equation. The value of t we have gotten is 30. The final step for solving for part B is to simplify our new equation to solve for n of t. What we first need to do in order to simplify this equation is to simplify what is in the brackets. After going to simplify what is in the brackets, our new equation is n of t is equal to 3.7 cos bracket negative 284 pi over 365 bracket plus 12. I have now found the cos of negative 284 pi over 365. Our new equation is n of t is equal to 3.7 times negative 0.76666 plus 12. The next step is to multiply negative 0.76666 by 3.7. Our new equation is now n of t is equal to negative 2.83366 plus 12. After doing this simple adding problem on my calculator, I have come up with n of t is equal to 9.16. The final step to completing this problem is to create a sentence answer. In order to come up with a good therefore statement, you must put your answer into the context of the problem. Here's mine. Therefore, on January 30th, there is 9.16 hours of daylight. Many jobs use trigonometry and equations similar to the one I used in this problem on a daily basis. For example, meteorologists use sine and cosine graphs very similar to the one I use in this problem to determine weather patterns at certain times during the year. For example, finding mean daily temperature. They place time in months on the x-axis and temperature on the y-axis and track the temperature patterns for each month and create a sinusoidal function and graph to track the changes in temperature throughout the year.